Although the death of the steam locomotive was written large on the wall of every station in North America by the mid-1930s, the obituary would have to wait until World War II was over. The New York Central Railroad was among the last to pay their respects. The big question on the minds of New York Central staff was, what would the next generation of locomotive look like? In his 1948 report, Paul Walter Kiefer, their chief motive power engineer, tried to answer that question. A practical evaluation of railroad motive power was an evaluation of the forms of motive power available in the late 1940s, and as such gives a good picture of the motive power situation at that time. In this video, we won't discuss the entire book. If you're a steam locomotive fan, we recommend that you get and read a copy in its entirety. It's about 50 pages in length. The next 3 pages show the table of contents. You can see that we'll be dealing with all forms of motive power contemplated for mainline use in the post-World War II era. The introduction explains the purpose of the report and what the report will contain. The author then explains the details he will deal with, such as availability, cost of ownership, capacity for work and performance. He identifies such things as acceleration, back to running speed, and the capacity of the machine, the locomotive, for straight-away running. He also stresses the need for improvement in motive power fuel economy. He begins with a discussion of the then most predominant form of motor power, the reciprocating steam locomotive. A self-contained power plant providing horsepower at the lowest initial cost of any type of locomotive then used or under consideration. Much should be done to increase its usefulness by providing greater freedom from failures and detentions en route and reducing the time now used for maintenance, servicing, and inspection. Otherwise, it may not be able to compete on its merits with other forms of motive power and will be faced with a restricted use and market. It's not the intention to trace the development of the reciprocating steam locomotive on our system, but to give a condensed and convenient means of illustrating its evolution during the last 2 decades. Locomotive development progressed as shown in Chart A and Table 1. If we look in this table at the maximum cylinder and drawbar horsepower, we can see that these values increased to provide for the demands made by heavier trains and higher speeds. Beginning in 1924, we have the K5 locomotive. Next, in 1927, was the J1. In 1937, the J3. In 1940, the L3. In 1943, the L4. And again in 1943, the S1. One thing the author makes note of is that with the S models, the single crank pin, one on each side, is subjected to a significantly higher piston thrust than in the previous models. Most railroads use some form of modification to the connecting rods and joints to alleviate this problem. Several roads took a different approach. In 1946, the T1 duplex locomotive was the Pennsylvania Railroad solution. It was basically two 440 locomotives sharing the same boiler. This was one way to allow for the further development of locomotives that would be able to use bituminous coal as a basic motive power fuel. The title Other Coal-Fired Locomotives gives a sense that railroads would like to hold on to steam locomotives for as long as possible. Likely the same could be said for the entire coal industry. In the constant search for better motive power, railroads have not confined themselves to the reciprocating steam or the present oil-burning diesel-electric locomotive. The advantages of large-scale use of bituminous coal are numerous and far-reaching, and for the retention and expansion of these benefits, several important steps already have been taken, and plans for new design of motive power are under development. Beginning in the mid-1930s and lasting to the mid-1950s, several attempts were made to develop a locomotive that made better use of coal as a fuel. This table shows several of the locomotives that were actually put into production or at least had a prototype built. Note that all the power sources are rotary and either steam or gas turbines. And all the output drives are rotary, being either direct mechanical turbine drives or electric motors. This feature would solve the crank pin thrust problem. In 1944, the Pennsylvania Railroad acquired its S2. It was a coal-burning, stoker-fired, non-condensing, steam turbine locomotive of 6/8-6 wheel arrangement, with direct drive mechanical transmission and geared for passenger service up to speeds of 100 miles per hour. If you ignored the lack of pistons, this machine had the appearance of a standard steam locomotive. The forward turbine was capable of delivering 6,900 horsepower and the reverse turbine 1,500 horsepower. The fact that two turbines were required made the reversing mechanism of the locomotive significantly more expensive than the use of the standard steam locomotive reversing arrangement. Compared with the reciprocating type, the turbine provides more power from a given boiler, a lower center of gravity, uniform torque, and absence of reciprocating parts and dynamic augment. Dynamic augment, also known as hammer blow, is a result of intentionally imbalanced counterweights in steam locomotive wheels used to offset the horizontal movement of pistons and connecting rods. It was intended to improve the ride quality. The disadvantages of a turbine drive are the high steam rate required at slow speed and the resulting effect on the staid boiler due to the extremely heavy demand. As diesel locomotives became more prevalent following World War II, the Chesapeake and Ohio Railway was one of several railroads that were reluctant to abandon coal as a fuel source. They saw coal-fueled steam turbine technology as a possible alternate to diesel. The C&O's engineering staff expressed concern that oil reserves would be depleted in the next 25 years. As such, they began the construction of 3 M1 coal-burning steam turbine units. These were substantially different from the Pennsylvania steam turbine locomotives. At the time of its construction, the M1 was the longest single-unit locomotive in the world. Since this locomotive's propulsion was by electric motors, the wheel arrangement was designated as C1 plus 2 C1 according to the AAR, Association of American Railroads designation. More on this in a separate video. Unlike typical steam locomotives, the M1's boiler was in the rear and its coal bunker was in the front. The M1s proved expensive to operate and mechanically unreliable and were scrapped in 1950. John Henry was the name given to the Norfolk and Western coal-fired TE1 steam turbine electric. Norfolk and Western received the Baldwin, Lima, Hamilton, and Babcock and Wilcox built steam turbine electric locomotive in 1954. It had a similar look to the C&O M1, but was shorter and weighed less. The boiler operated at 600 psi and delivered steam at 900 degrees Fahrenheit. The traction motors and generators were Westinghouse manufacture, and it rode on 4 3-axle trucks. All axles were powered, so the John Henry was referred to as a C+C-C+C locomotive. This locomotive utilized dynamic braking, in which the power is shut off to the motor armatures, but the motor fields are left energized. The motors then act as generators and feed the braking power developed into resistor banks. The energy taken from the locomotive's motion is dissipated as heat. With the use of pulverized coal and a fire tube boiler, these locomotives bore little resemblance to the steam engine we usually think of. They were more like a thermal power plant on wheels. The TE1 was in service for only 3 years. Its demise resulted from reliability issues. Among other things, coal dust contaminated the electrical equipment and interfered with boiler controls. This resulted in the locomotive being scrapped in 1958. With the experience gained in the production of turbines for the jet engines of World War II, it was natural in the post-war years to think of them as a source of power for railroad locomotives. Early in 1945, 6 railroads that had a vested interest in coal-fired locomotives formed the Locomotive Development Committee to foster the development of a coal-fired gas turbine locomotive. Several unique features were developed for coal pulverization, for combustion, and for disposal of fly ash. Coal of regular locomotive size was to be dried in the stoker and fed from the bunker into a hammer mill where it would be crushed. The crushed coal is then conveyed to a coal pump where it's pressurized and fed under pressure to the atomizer nozzle in which pulverization takes place. The removal of fly ash is of the utmost importance, as tests have shown that if this function is not properly accomplished, serious abrasion of the turbine blades will result. While the Locomotive Development Committee planned to purchase 2 coal-fired gas turbine locomotives by 1957, none were built and the project was canceled, citing poor business conditions, presumably brought about by the advent of the diesel locomotive. But the Union Pacific continued to experiment with gas turbines. In the early 1960s, UP shops constructed a monstrous 214-foot, 3-unit, pulverized coal-burning gas turbine electric. This locomotive was designed to burn Union Pacific-owned Wyoming coal supplies. The diagram shows a coal-fired gas turbine generator set. Beginning at the top left, the coal is screened and then pulverized and then burned in the combustors. The products of combustion is a gas which travels to the separator where the ash is removed. This is the most crucial part of the process. Without virtually total removal of the ash, there would be destruction of the turbine blades. The products of combustion then travel to the turbine, causing its blades to turn. The turbine shaft drives the compressor, which feeds combustion air into the combustors, and also drives the electrical generators, which in turn drive the locomotive's traction motors. A turbo generator set is a complex device requiring specialized maintenance personnel. The fact that it was even considered as an alternative to the diesel locomotive is an indication of the powerful lobby the coal interests had. It bears a great resemblance to the systems designed by Rube Goldberg. Judging by this portrait of the artist, he may even have been one of the Locomotive Development Committee members. Looking back at the table of contents will show that we have covered only about half of the report. We looked at the introduction and the reciprocating steam locomotive. We also looked at other coal-fired steam locomotives and the gas turbine locomotive that ran on coal. The rest of the report evaluates other motive power. But since our focus was on coal-burning locomotives, we'll skip to the conclusion. The author says that the need for better performance is manifest in any of the fundamental aspects which it has been the author's endeavor to analyze, with the result now summarized in Table 4. The acquisition of new forms of motive power should be authorized as they are developed and made available. Table 4 provides an evaluation of all the motive power based on availability of the unit for service, overall cost of ownership, capacity for work, and efficiency. To maintain the supremacy of rail transportation, modern locomotives and cars must be acquired as conditions permit. Whether King Cole liked it or not, modern locomotives would not be steam locomotives. The steam locomotive was dead.